so I don't have to do this later. All right. So we are going to look at your electricity notes today, so everybody has that. The very first thing that we are looking at is electric charges. And this is something, again, that's review. Remember, when we get to magnetism, magnetism has a north and south pole. Electricity has positive and negative charges. The same charges, if they are the same, two positives or two negatives, they are going to repel each other. So you can see these diagrams right here. Two positive charges are going to push away from each other. Two negative charges are going to push away from each other. If I have opposite charges, they're going to pull towards each other. So positive and a negative. If you've ever noticed when you're setting up a toy, it probably took you when you were 4 years old putting in your batteries to your toys that you got for your birthday or Christmas or something. If you turn the battery the wrong way, the toy wouldn't come on, right? And you learned real quick that there's a positive end and a negative end, and you had to put that positive where it says positive, right? You knew that to get your toy to work. So you knew how to set up a circuit from like the time you were 4 years old. So those positive and negative ends have to be aligned so that it will end up pushing those charges through and your circuit will work. So you have something called an electric force. And again, that push is coming from that electric force of why if they're attracted to each other or they're repelling each other. So that attraction between opposite forces, a positive and negative, or that repulsion is called that electric force. It gives you a force field around it. Okay? So it's that attraction or repulsion between electric charges. And that is called your electric force. Then you have an electric field. Now, an electric field is a force field. It's a field that's the area around an electrically charged object. So your phone is an electrically charged object, and it has an electric force field around it. It has electric field. And if you've ever stayed at a hotel and they've given you the little hotel room keys, or you've had tickets to somewhere that has like a magnetic strip on the back, if you've ever stored those little things, including, it could possibly even be like your debit card or your credit card, if you store that directly in contact with your phone, there's interference there. Your phone is a stronger field than the little magnetic strip on the back of those cards. And so that the electric force field is going to rearrange that magnetic strip, and so your hotel room key won't work, or your tickets won't work, or whatever. That's that little card, because it's pretty weak. It's a little weak magnetic field. So there's an electricity and a magnetic interaction there. So, y'all ever done that? I've done it. Put my key next to my phone. Never? Not been? Okay, well, y'all are lucky. So in diagram, we can't see, like you can't look at your phone and see where that electric force field is around it, right? You can't see that force field, but it's there. And in diagrams, the way what we do in science to see if you understand stuff, or the way they test us, or the way that we look at things when we're learning stuff, is diagrams. And they draw these force field lines. So they show the direction of the force. You can see the positive ends have the pushing force. The negative ends, that's pulling in. So the force field is pulling inward on the negative end. And if they're stronger, they're drawn closer together. So you can see right here at the charge itself, because those lines are close together, it's stronger. And then as you get further away, the lines are wider, and that means that the force field lessens and lessens. So we've got two types of electricity, really, two basic kind of types. You have static electricity, which you probably talked about a lot in middle school. You talked about charges building up on objects, positive and negatives, and then how they eventually discharge or zap. So lightning, for example, is really static electricity in the environment. It's really on a really large scale, but it's from positive and negative charges building up on objects, on clouds or the ground or cloud to cloud. And then it eventually has to discharge because it wants to get back to neutral. Socks coming out of the dryer when they're hooked to, a blanket or a, what? You don't like that? Yeah, and you pull them apart and you just hear it snap. And especially in the winter time, sliding across the bleachers, or you're getting out of a car and you touch something and it zaps you, or the buggy in the grocery store, you get zapped by static electricity. And it builds up in the wintertime more than in the summertime because there's not as much moisture in the air. So the air itself is a little bit more conductive of electricity in the wintertime because it's drier. So if it's drier outside, you'll notice more static electricity. We're going to talk mostly about current electricity this year because all of our standards come from current electricity. So our current electricity, what it is that constant flow on a wire. And it has to come from somewhere, some type of voltage source. So we see power lines, obviously. When your phone is charged up, that's a current electricity. Even when your phone is not plugged in, it creates a little circuit inside the phone itself from the battery. It goes from the battery, from one side of the battery, through all your stuff and back to the other side of the battery. So we're going to be talking a lot about current electricity. So let's talk about electrical currents and what they are. And of course, we're going to be calculating the current and the resistance and the voltage. Okay? So electrical currents, what they are their charges, right? Those positive and negative charges. And they are what make that flow. It pushes those electrons along that wire, pushes the charges along the wire. So two like charges will move away from each other. If they didn't have that force field, then there would be no reason for them to move. The rate of the flow of charges moving through a wire is called the current. So how much ever that the charge, or how many ever charges basically you're moving, is your current through your wire. And the SI unit for current is called an ampere. Now, I always say ampere because we're in South Georgia, but it's like ampere. But I feel weird saying that, so it's ampere. And its symbol there, it's instead of like putting M for meters, its abbreviation is just an A, capital A. And so anytime you're looking for a current, you're going to be reporting it in an ampere. Okay? And it's like that push. It's what's pushing it through. Way back when they called that, before they started talking about current, they called that electrical pressure in the wire. It's like water pressure. Think about water coming out of a hose. If it's highly pressurized, you can turn that nozzle and make it really, really hard, or you can make it spray out like that. So this was called like electrical pressure. So you can think about electricity running through wires as you can kind of think about water running through a hose. It's an analogy. Of course, water and electricity are not friends, right? You don't want to get water on your electrical circuits and all kinds of stuff. So we've got this potential difference, okay? Potential difference is kind of related to potential energy. You know, how much energy does it have? So electric charges will move from areas of high potential energy, that's important, high potential energy, to low potential energy. You can almost relate this. It acts very similar to like air masses. Air masses move from high pressure systems when you learned about weather, and they want to be low pressure, just like you. If you are in a highly stressful situation, what do you want to do? If you're in a highly stressful situation, do you want to be there? No, you don't. You want to go somewhere and chill out. You want to go to the beach. You want to go on vacation. You want to break from school. So electricity, right? I mean, we're all like that. Highly stressful situations, they don't sit well with us, right? Electricity is the same thing. So you have areas of high potential energy, which are like high pressure. They've got those electrons stashed in there, smushed in there, and they're wanting to get away from each other, right? And so that's what's creating that push. So we've got, it wants to go to a low stress. It wants to go to low potential. It wants to chill out, just like we all do. So we kind of act like electrons, believe it or not. All right, so the difference in these two areas is known as your potential difference. So if you notice that it's measured in volts. So if you have a higher voltage battery or a higher voltage outlet, if you have higher voltage, you have a higher potential difference. So therefore the push is going to be greater. That's why it's more dangerous, right? You get a higher push. It's more stressful of a situation that it wants to get out of and get to a less stressful environment. So the higher the stress, the more frantic those little electrons get, and they want to get out of there bad. And so higher voltage means you have a higher potential difference, okay? And it's measured in volts. Then we have something called resistance. And a resistance is going to slow down that current a little bit on the wire. It's going to slow down that flow of electricity. Sometimes we need resistance and we put them in there on purpose so that we don't have an electrical shock. But if you think about plugging a lot of stuff in, if you think about this room or your bedroom or something being one big circuit, if you have too many things plugged in, you are creating a lot of resistance on that line. You agree with that? Yeah. And sometimes if you have too much stuff in there, it'll trip your circuit breaker. But every time you add something to a circuit, you're adding resistance. I think about too, it slows it down. It's like internal friction. Think about your phone. Your phone's battery only lasts so long before you have to recharge it, before it dies. And we're all well too familiar with we need our phone and it dies on us, or it's about dead, or whatever. And you see that little battery going down and down and down. And you know it's true, the more stuff you have open in the background, then the quicker your battery's going to die, right? Or the more, if you're playing a game, or if you got one social media thing up and you got another one in the background and people are texting you, your battery's going to die quicker. And those types of things you can think of as resistance in that little circuit. It's slowing down the current. It's creating some internal friction on your phone. And so you always know that you go to that background and you should try to shut everything down, especially if you're trying to save your battery, right? So you can kind of think of resistance like that if you think about something that we have in our hands all the time. Now, this is a little bit different because this is a Greek letter. We've used the Greek letter delta, right? And this is the Greek letter omega, O, right? It's the Greek O. And it is the symbol for ohm. And an ohm is the unit, the SI unit of resistance. Again, just like we measure distance in meters, we measure resistance of electricity in an ohm. So it might have 4 ohms of resistance or 10 ohms of resistance. The higher the number, the bigger the resistance is. Okay? So that's an ohm. Now, here is the formula. And we're going to calculate today a little bit. So you have voltage, current, and resistance. And what this mathematical formula does is it shows you the relationship between voltage, current, and resistance. So think about it. If I have a higher current, then I'm going to have a higher voltage. If I have higher resistance, I'm going to have a higher voltage. If I have a lower voltage, I'm going to have a lower current or a lower resistance, one of the two. So again, we've drawn the triangle so that whenever you're looking for, you've got voltage is equal to current times resistance. So if you set it up, then cover up voltage, you end up with current times resistance. And the symbol for current is an I, which is kind of weird. And I don't really know why that is. I just haven't ever taken time to research it. I'm sure if you want to Google it, why is the symbol for current an I, you'll find lots of answers. I don't know. If I'm looking for the current, which is I, then I would take the voltage and divide it by the resistance. If I'm looking for the resistance, it's the voltage divided by the current. Right? Same. So it works, that formula works the same way. Now let's talk about some things in a circuit and what the parts are, because the rest of this week we're going to be working in PhET simulation and in real life lab, setting up circuits and working with current and seeing how all that works. Okay? So some things that we have to think about when we're setting up our circuits are conductors, obviously. If we don't have conductors, you don't have wires, you don't have a circuit. Electricity has to flow on a conductor. And conductors are metals. Some good conductors are things like copper and silver and iron and aluminum. And they have low resistance. So you have different type of wire. Is anybody interested in electricity? Electrician, do you have an electrician as a family member, or you've wired some stuff at your house? Huh? You're scared of it? It scares me a little bit too. My stepdad worked with electricity at one point, and he had a wire that wrapped, it's always scarred me because he had a wire that wrapped around his arm when he was doing something and it blew up. And so he's got a big, he had to have skin grafts and stuff, so his from when I was little, I'm always like, it's always made me a little nervous too. Now I've rewired my ceiling fans in my house. I've replaced some lights and stuff like that. But I'm not too keen of electricity. But you can make really good money. Did y'all know that? I think it's pretty interesting. And it's like a tech degree. So you can go for free to college, get your tech degree in electricity, and you can go wire houses and, businesses and all kinds of stuff. And so you can make pretty good money and not have to sit behind an office desk either. You can go out and, So I think it's interesting. I'm just a little nervous around electricity sometimes. So you have to have conductors, but you have different gauges of wire and all that kind of stuff. So there's some math to it too. And I'm not a pro by any means when it comes to electricity, but you have different types of wires that you get for different jobs, depending on what you're wiring. But then you also have insulators, and this is important for our part if you're scared of electricity. You want to make sure that the plastic around the wires is not frayed or broken. Now is the time we're all getting out our Christmas lights and Christmas decorations, and we're putting them outside and on trees and stuff. So one of the things they'll tell you in the safety manuals is to look for, or don't use them, if some of those insulators, that plastic, is gone and you can see the wire. If you can see the wire and there's not an insulator there to stop it, has high resistance, right? If it's not there to stop it, then you could have sparks. And if you are putting out Christmas lights into your yard and you've got pine straw and it's really dry, then you could have a fire. You don't want that. Or if you're putting it on a Christmas tree, a real Christmas tree, and it dries out and there's a part where that spark can be. It doesn't take much for a Christmas tree to ignite. So those are just some things. But we do like those insulators. And again, probably your phone cord, my phone cord is frayed a little bit. My charger cord, bless you. And I can see that wire. Probably it's not the most efficient, but I have it. Anyway, all right, parts of a circuit. When we're setting up our circuits, and again, tomorrow you're going to have a FET simulation with your circuits. You have conductors, obviously your wires, and when you're setting them up in real life, if your conductor is not touching your conductor, you don't have any electricity flowing. So you have to make sure metal touches metal. Then you have resistors, stuff that slows down the current. So your insulator that's wrapped around the wire is going to slow down your current. You can add little resistors, and I'll show you what those look like tomorrow on a FET simulation, to slow down your current. If I put too much current through my conductors or wires, I can overheat or short circuit my system. I can blow out my light bulbs or fry whatever I've got plugged in. Right? So like if I have a computer plugged into too much voltage source, it can basically fry the computer and just zap it and it's gone. Or the TV. We don't want that to happen. You want to have a safe amount of electricity running through it so that your device works, your load or device works and doesn't fry it. Right? You have your voltage source, either an outlet or a battery of some sort, and then you have some type of control. When you have a switch on a circuit, like a light switch, you have control of that circuit. When that switch is closed, you can have that electricity flow. When it's open, you put a gap in that circuit, okay? And so your electricity doesn't flow. So I'll show you what that switch looks like. Did y'all build circuits last year with the wires? So you're familiar. All right, these are, and I put this diagram on your notes, these are the components of a circuit, and when we see them, or when you see a components on the circuit on an EOC, it's going to look like this. Do y'all remember diagrams like this on last year's milestone test? Yeah. So they don't draw them all nice and realistic. They draw them in diagram like this. So you notice that A is labeled, and what A is your battery in this circuit, okay? And that's going to be shown by these little lines. And then you have B, your switch. In this case, this switch is open. So is electricity flowing through the circuit or not? Yeah. No. It's not, is it? Because this is open. If you have a gap in there, you don't have electricity flowing from part to part. It has to touch. So if that switch was closed, then your electricity would flow. Your light bulbs would be on. But that switch is open, so there's a gap, and electricity, unless you have really, really high voltage, it's not going to jump the gap. So you're not going to have your light bulbs on. That's off, and if I closed it, that would be on. And then my light bulbs are drawn like this. And a lot of times in diagram, a light bulb is just the symbol that your circuit's working or not. And then your resistors look like these. And again, these are on there to show you can slow down a current. You can create friction. You can slow it and make sure it's safe to come through your devices so you won't fry them. All right, then there's two types. Of course, you built these last year. Probably did you build a series and a parallel circuit? Yeah, and you saw. And so this is just review. This is nothing new. But your series circuit itself is where it travels, remember, one way. It's like a one-way street. It's a single path. And then if you have one break in that circuit, if one of those light bulbs goes out in that circuit, it's done. I always think about a group of people like playing Ring Around the Rosie or something. They're holding hands, right? Group of kids playing Ring Around the Rosie. They make a complete circle. If somebody lets go, you have an open circuit. That's just like a series circuit. If somebody lets go, you don't have a full ring around the rosy. You don't have that electricity flowing through. So one break, any break, is going to break the circuit. So if the electricity can't get up and go through that light bulb because it's burned out, you don't have a circuit. All your light bulbs will go out. The current is the same throughout the circuit, so the lights are in equal brightness. There's not going to be one section that's brighter than the other, one that's brighter than the other. Each device is going to receive a fraction of the total. So whatever, like let's think about Christmas lights. If I keep adding Christmas lights to a strand, if it is a series circuit, they're going to get dimmer and dimmer the more that I add to them. They used to be all series circuits, but now a lot of them are wired in parallel, and that doesn't happen. But that's what you can think of. 300 strands of light should be dimmer than a 100 strand of lights. And so all lights get dimmer as they are added. And then a parallel circuit is where the current travels in multiple paths. So you have different ways. You don't have to just go in one direction. You can go through different loops. You have a different way to get to and from the battery. And so one break, if you have a light bulb that goes out, your flow doesn't stop. So think about it. Is this room right here measured or wired in series or parallel?
Parallel.
It's measured, it's wired in parallel. Because if I have a light bulb that goes out, all my other stuff stays on. So it is a parallel circuit because my electricity is not just going through everything. Because otherwise, if it was series, a light bulb would burn out and everything would go off. The computers would go off, all the lights would go off, and that just doesn't make sense. It's not very user-friendly because we've got a lot of stuff going on. So what's going to happen is the current varies in different branches. You can actually have different voltages and different amperes going through different branches. It's going to take the path of least resistance. Electricity is kind of lazy. It's kind of like us, you know. Again, we want to go from high pressure to low pressure. So does it. It wants to go from high concentration to low concentration, and we want to take the path of least resistance. We want to get the easiest way, right? We see the finish line. We want to get there the easiest way. Electricity does the same thing. In a parallel circuit, the bigger light is going to be bigger lights will be dimmer because there's more voltage being pulled through. Each device receives the total voltage, and there's no change when lights are added. So if you have parallel circuits, I can have a strand of 800 lights that are going to be just as bright as if it were 100 lights. Okay? No change there. And then your household circuits is a combination of a bunch of parallel circuits that go along, and they're almost as parallel circuits wired in series, really. Too many devices on something can cause a circuit or cause wires to overheat. And we have some devices that are going to help us that I'm going to put up here in just a second. Have you ever tripped a circuit breaker in your house? Mm-hmm. Yeah. So you have to go to that circuit breaker box. And that circuit breaker box is there because too much voltage is running through those wires. It's just there so we don't have a house fire. So what happens is, this is kind of a summary here. If I have flowing charges on a wire, that's kinetic energy, right? We haven't talked about kinetic energy and potential energy in a while. But kinetic energy, because I have movement. It's just like if all of us got up in here and we started doing jumping jacks and burpees and all kinds of stuff, our temperature is going to go up because we have kinetic energy. Same thing on a wire. There's a lot of movement, so you're going to have kinetic energy, and kinetic energy is going to give off heat. So that's why wires get hot. That's why when you have your phone and it's on and you're running it, or a laptop and on it's running, it gives off heat because you have kinetic energy. You have electricity that's actually moving, even though you can't see it. So these circuits can overheat. And in our houses, we have things like fuses or circuit breakers. And those are there for our protection, because what happens is there's a little pieces of metal in there.
Young Wynn needs a report to the front office. Young Wynn needs a report to the front office. Thank you.
And in a fuse, that metal is going to melt at a certain temperature. So that's telling it if it gets too hot, it'll melt, it'll break the circuit, it'll cut everything off. Same thing with the circuit breaker. The little metal that's in there will bend, and that'll break the circuit, and therefore you'll have to go and trip your circuit breaker box. All right, so here's what we're going to do. That's the end of your notes for today. I'm going to give you your, Jamal, will you give everybody one of those? I'm going to give you some problems. And on this sheet, we have it set up. We've got our three variables there. And you notice that it also has the triangle. Okay. And then it's got a place for you to put the equation. And then it's got a circle. We're just going to put our answer in that circle. Okay. So if I look at the first one, first of all, let's write the equation right here. V is equal to what? IR, right? That's kind of the basic equation. And there's my triangle. I don't always have to use it in this way. I can change it around, right? So if I look at what's given to me, it says there are 28 ohms of resistance. So where does that go? What is that? My resistance, right? Felt like that was a trick question. 28 goes here. 28 ohms, right? And I kind of draw my ohms like that. Then it says it's plugged into a 110 volt circuit. So is that voltage or current? Voltage, right. Voltage is voltage. Almost too easy. So you got 110 volts as your voltage, right? And so it says how much current. So that's what I want to know, is how much current is that going to be. So this is my formula. And I've written it in a triangular form so that you can rewrite the formula for what your current is. So I don't have to use this formula like this. I can rewrite it for current. And my current abbreviation is which one? V, I, or R? I. So if I am looking for I, what formula am I going to use? V divided by R is exactly right. So my voltage is 110. So I is equal to 110 volts divided by my resistance of 28 ohms, right? So what's 110 divided by 28? 3.92. 3.92. So I'm just going to round it to 3.9. And I'm going to be done. Now, is that my answer?
Yes. Wait, hold up.
I have to put an A, is exactly right. So it's 3.9 amperes. So I'm going to put 3.9 A in my circle. And then I'm done. It's the same format as kind of all of our others. Once you plug in, it's 6th grade math. So, and these are real straightforward. You don't even have to hunt for these. So what I want you to do is I want you to do 2 through 9. And when you're done, you should be able to put that in the box. If you're having specific issues and troubles, just let me know. And I will come around and help you.